These are the different types of graph that you might encounter during IB chemistry. The ones on the right are the most easily dealt with because they are linked in with what we've been looking at already. So, for instance, if you increase the concentration of a reactant and there is no change in rate, so this is doing several different experiments, and changing the concentration doesn't change the rate, then it's zero order. You get a flat line. If you're changing the concentration over a series of experiments and the rate is directly proportional, then that is first order. And if you are changing the concentration and you get a steep increase in the rate, then that will be second order. Now, occasionally you will see a graph of rate against concentration squared, and if that graph is a straight line, then it tells you that the order is second order as well. So this is all a little bit of, I hope, relatively common sense. Now the ones on the left may take a little bit more work on your part. So here you are measuring the concentration of a product, concentration of a reactant or something proportional to that reactant concentration with time. And you're plotting that. If you see a graph like that from your plot, a straight line going down diagonally, then the rate the rate equation includes zero order with respect to that particular reactant. And this next one, you get a smooth curve with a constant half-life. So I'm plotting the concentration of a reactant or something proportional to that against time. And maybe we'll see a little bit more what's meant by that when we look at the practical in a second. Now, first order reactions have what's called a constant half-life. If you know what half-life is from physics, you've got a bit of a head start on everybody else. But the half-life for our reactions here is nothing to do with radioactivity. It is to do with the concentration. So let's say that was a concentration of 1.28 moles per decimeter cubed. You would then, on your graph, find 0.64 moles per decimeter cubed, draw a line across and a line down. And the time taken for the concentration to fall from 1.28 to 0.64 can be deduced from the graph. That is a half-life. Then you have to do it again. You go from 0.64, line hopefully you've already got drawn in, construction marks, but this time down to 0.32. And you find the time for it to have fallen from 0.64 to 0.32. That's another half-life. You then go onto your graph to 0.32 to 0.16 and find the time for that to occur. You have then taken three different half-lives, one after the other, and for it to be first order, those values should be pretty much the same. It's very difficult in experiments to get them identical, but they should be very similar. Now, if you find three half-lives and they are not constant, then you have second order. So now, what you're going to do now is, again, look at an experiment sheet, and you're then going to try and deduce the order from the results. Now, In the experiment, I'm going to give you results for the volume of a product, which is proportional to the concentration of the product. And then there's a sneaky little way to convert that concentration of a product into the concentration of a reactant. And you'll see that in the experiment. These graphs most often come up in multiple choice questions, and the key thing to getting the right answers is usually looking at how the axes are labelled. So please look carefully at how they are labelled before I go. Okay, so rate against concentration on the right hand side here, that is the concentration for several different experiments. So it's the initial concentration. And on here, you are following the concentration of a reactant during one single reaction.